recorded. So, all right, so now we're recording. So what I was saying is that it's really important to understand that there is this evolution of ideas that happen. And OpenFlow was the first set of protocol that was proposed back in early 2010 or late 2000s. And like the hardware targets were not where they are right now, right? So the type of applications, the type of design choices that a lot of network operators made at that time, if you think about those same set of problems now, you might not choose the same solution that they chose, right? And that's because the technology spectrum or technology ecosystem has changed or evolved significantly, right? So when people were working on STX, when people were working on B4, they were constrained by these design choices that, like we don't have a hardware target that we can just go out and, deploy in our network that is going to support, terabits of data rate and support these millions of TCAM or SRAM entries in the data plane. So those type of targets didn't really exist, and that type of flexibility didn't really exist, right? But we did talk about the protocol independent switch architecture, which is a hardware data plane target that offers a lot more to the network operators. That if those targets were available back when people were building B4 or back when people were building STX, the design choices would have been completely different. The design constraints that they were operating on would have been completely different. So, from today's lecture, we will focus on this new use case that I would say is, even more, recent compared to all these ideas that we discussed before about the software-defined wide area network or software-defined internet exchange points. The telemetry is something which is the holy grail in networking right now, right? Because the evolution has been that first we want to enable software-defined networking in our data center networks, in our wide area networks, because we want to maximize the utilization. We want to enable flexibility in how or what type of policies I want to apply and still make the best use of limited resources that I have in the network. But now the focus is more towards the towards this ultimate optimization that we want to do, which is that now you have all this control and flexibility in the network. You have all this programmability that is enabled by the network, but that comes at the cost of added complexity, right? So I can push things further and try to squeeze in more like packets within the network, and with the same set of resources, I might be able to optimize my network further, but that just complicates the network a bit more, which means that the set of tools that the network operators were using or relying on before are no longer useful, right? So the type of tools that the network operators had to understand what's really going on in the network, they're not as useful now, right? And that has motivated this new direction in the networking community to think about or develop new set of tools and techniques which can provide better insights about what really is going on in your network, right? And then use that insight to drive decisions, right? So, the eventual goal that the networking community sees is that if we want to do the best possible job with the limited set of resources that we have, we really want to optimize each and every opportunity to send traffic from one point to the other. But that means that we might have to make very, very complicated decisions. A lot of those decisions might be beyond human cognition as well, right? So the type of decisions that we have to take might not be, like possible for a human operator to, put it in their brain and think about, okay, like I'm going to do X, I'm going to do Y. These decisions need to be automated, right? So this is the ultimate goal that the networking community is pushing for. They're envisioning the design of self-driving networks that can run themselves without any intervention from the human operators, right? But to enable or realize those goals, it's very, very important to extract insight from the network that are going to drive these decisions, right? So think about a closed loop system that you're understanding the current state and then trying to drive decisions how you can optimize the use of these networks. How can you optimize the KPIs that you have for different type of applications that are using these networks, right? So with that context, I think we are, like that maybe gives you some sense of why understanding what's going on in the network is important, and why we are going to focus on the telemetry part of as a use case for software-defined networking. And something that I really want you to understand is that the telemetry or like the analytics that you can do on the network traffic was not the first use case that people really envisioned, right? So the creators of like PISA targets or the RMT targets, reconfigurable match action table targets. They never envisioned that telemetry is going to be the killer application that's going to drive the adoption of software-defined networking or the adoption of PISA targets in networks, right? But over time, and this is the beauty of all these open source systems or all these open systems in general, is that once you put it out in the community and then other people start using it, then there is a lot more value addition to these set of ideas, right? So people had some other vision about how these PISA targets can be used, but they just made it accessible to a bunch of researchers, and that enabled exploration of completely new use cases that others didn't even think about in the past, right? So that's where the network telemetry kind of like fits in. That network telemetry is important. The network telemetry by definition means to extract remotely metrics of the network from the network, right? So in some sense, kind of like, extract some key metrics from the network in a remote sense. That is telemetry. And there has been a lot of work in this space conventionally also. When you think about networks, maybe you're aware of tools like Wireshark, you're aware of tools like NetFlow. So these are the traditional tools that the network operators were using. But we will discuss today that why such an approach is not such a feasible thing when we're talking about a network as big as Microsoft or as big as Google. These are not the type of tools that you can use or rely on. Okay. So I hope this sets the context for what we're going to talk about today. So when we talk about network management, and this is probably a figure that we have seen before as well, that the network operator wants to like manage this network as efficiently as possible, but then the task is kind of like very overwhelming because there are all these different type of events that are happening in the network. Those events can be outages in different parts of the network, and you need to be aware of those outages. And there might be some congestions that are happening within your network, or there might be congestion events that are happening remotely. And as a network operator, I need to be aware of all these different type of things so that I can, drive my decisions about how I want to, like define the policies for the network. And then I might also be a victim of any type of cyber attacks, right? So I don't know if you folks are exposed to cyber attacks, but maybe anyone can give me an example of a cyber attack that you know of, that you have heard of. Have you heard of DDoS attacks? So can anybody explain what DDoS attack means?
Like send too many data, handle.
Right. So that's kind of like one description of DDoS, that it's DDoS, like DDoS basically means denial of service, right? So if you overwhelm a particular host, if you overwhelm a particular network, then they are denying, you're in some sense overwhelming them enough that that's denying service to other benign or genuine users, right? So that's a DDoS, that's a DOS. But DDoS is like, when you launch this attack in a distributed fashion, that you're not just launching this attack from one location, but you're launching it from multiple locations, attacking it from multiple locations, then that's an example of DDoS, right? And that's a very common thing. You'll be surprised how common these type of attacks are. At even UCSB, being a campus network, you would imagine that people should not be targeting us, but we are victims of these type of attacks almost on a daily basis. And people, like when I say people, even these are attackers who are always looking for opportunities of, any type of vulnerability that we have on the host here. There are all these, scanning going on our campus network to explore if there are these open vulnerable ports on any of the servers that can be compromised. So we have to have a, even as a small campus network, we have to have our defense mechanisms set right to make sure that we are protected against all these type of attacks, right? But DDoS attacks happen, when like there is some specific targeting of a particular specific service. Maybe somebody figured out vulnerability in any of our grading servers, and then when the grades are supposed to be released, somebody can attack those servers, right? So this is an example of targeted attacks that sometimes the attackers have. But in general, most of the time we are victims of low volume attacks, in which people are just exploring the functionalities, like the networking functionalities across different hosts on the campus network to try to figure out if there are any known vulnerabilities out there. All right. So these are the, as a network operator, these are the things I really need to know, and I really need to worry about. And it's also important that I'm able to detect these type of network events in real time, right? If I know that there is an attack going on tomorrow, then that's not going to solve my problem today, right? And like that's why I would say like being a network operator is also a very stressful job. It's a sometime 24/7 job. You should meet some network operators at UCSP. They're overly stressed about making sure that networks are always operational. So I have a lot of respect for them, but at the same time, that's also a motivation for a research for a lot of people that, how can we make sure that these network management tasks are as automated as possible so that we are not stressing these human operators in between, right? So there is this clear requirement that we want to detect these wide range of network events in real time, right? Let's try to understand this monitoring requirement with an example of a specific type of DDoS attack in more detail. So consider that the victim is sitting, maybe you can think of victim as a host inside UCSB's network. And there's an attacker who decides that I'm going to DDoS this specific host, right? So what they can do is that they can send a DNS request to DNS resolvers across the internet, right? And there are a bunch of DNS resolvers who are not patched to the latest software that should be used, and they're using older versions of the software. So it is possible to spoof the request that you send to these DNS resolvers, right? So when you send a DNS resolver, what do you say? You say like, tell me the IP address of this domain, right? And when you send that request, technically you send your IP address so that the resolver knows that the response has to be sent back to you, right? But if I am an attacker, what I can do is that I can like spoof the source IP address of the packets that I'm sending. And I can say that, okay, like, change the source IP from the attacker's IP to the victim's IP. So now when the response is coming back, it is going to the victim IP address, right? And if I do that enough, like if I, rather than sending just one request, if I send millions and millions of requests, then all those millions of responses will be coming back to the victim, right? And that's how the victim's network can be overwhelmed. But now you must be thinking that, how is this really an economical attack, right? Because the attacker is sending, for every one response that it is going to the victim, the attacker also has to send one request, right? But there is this notion of amplification that I can make sure that there are these tricks that I can play with the DNS protocol and make sure that the size of the response is extremely large compared to the request, right? So that is called DNS amplification attack as well. So reflection meaning that it's sent to a resolver and then reflected to the victim. And amplification means that there is a significant difference between the size of the request versus the response, right? So this is how these attacks happen. Now, if I'm a network operator, hosting this, managing this host, and I want to know whether any host in my network is a victim of such an attack or not, I need to, keep track that is there any host that is receiving DNS responses from many distinct sources within some time window, right? So, maybe I want to analyze this every 1 hour, or every 5 minutes, or every 3 seconds to count that how many DNS responses are received by any host in my network from distinct set of sources, right? And this is just one example. When we talk about writing these type of analytics that I want to run in my network, notice that I'm saying that I want to look for DNS responses. But DNS, when I say DNS responses, it is one way of specifying a portion of traffic that I'm interested in, right? But then there are so many ways in which I can define what portion of traffic I'm interested in. I might be interested in, traffic identified by the IP addresses, traffic identified by the protocol that it is using, the payload type, the type of devices, location, et cetera, right? So there are so many ways in which I can express that which portion of the network traffic I'm really interested in, right? And then the second part of this query is that we want to know how many distinct sources are, these responses are coming from, right? So in some sense, what I'm doing is I'm trying to extract aggregate metric from the network traffic that I'm specifying, right? So in some sense, I'm expressing some type of filter that, hey, this is the portion of traffic that I'm interested in. And then I'm extracting some type of aggregate metric. In this case, it is the number of distinct sources, right? But then there are so many ways in which I can express what type of metric I'm really interested in, right? So I can say like maybe average jitter, max jitter, min jitter, a distinct number of hosts, the traffic volume, the delay, loss, etc., etc. Right? So in some sense, what I'm getting at is that when I'm a network operator, and if I want to know what really is going on in my network, I want to run a wide range of queries in my network to figure out whether there is any problem going on or not, right? If I want to figure out if there is some type of congestion going on locally or remotely, I want to figure out if there is an outage going on. I want to know if my network is a victim of any type of cyber attacks or not, right? And to express all these type of, analytics tasks, I need to, explore, like, and express that what portion of traffic I'm interested in. And as we discussed, that there are so many ways in which I can express that. And I need to express what specific metric I want to extract from that portion of traffic. And there are so many metrics that I might be interested in, right? So there is clearly a strong need for flexibility, supporting flexibility in types of analytics or in types of tasks that I can, or queries that I can run in the network to figure out what exactly is the state of the network or what exactly is going on in my network. So, like researchers have debated on this over a long period of time, like, a couple of decades, people have been discussing that, what is the right abstraction at which you should be expressing these analytics tasks and, or like, at what granularity we should be expressing the queries for the network, right? And, for your reference, if you know something like, Snmp. Have you heard of Snmp before? Somebody has? You have? Okay, tell me what is Snmp. That is SMTP. Okay. Anybody else? Okay. So, like Snmp is, like a set of protocols that are used for managing network devices, right? And you like traditionally they're used for sending the configuration to the devices, but you can also use them to query some statistics from the devices, right? So that is a traditional tool or conventional tool that is supported by a lot of network devices, since the inception of network devices, right? So whenever Cisco, Juniper, all these devices were heavily used in the network, they were all supporting this SNMP protocol, where you can send a query to the network device and ask, like, okay, for a particular network interface that you have, how many packets did you see, right? And that is one approximate query that you can run and get a sense of how busy my network is, what is the type of link utilization that I have in my network, right? But this is a bit coarse-grained query that we are able to support with SNMP, because I cannot tell that how many packets did I see for a YouTube traffic, right? I can only say how many packets did I see for the entire link or entire interface, right? So I don't have that type of flexibility to specify which portion of traffic I'm really interested in, right? So what I was getting at is that there has been a debate, or back and forth in terms of what is the right level of detail at which we should be expressing these analytics tasks, right? So earlier people were just expressing or extracting this information at the granularity of link by querying the interfaces, and SNMP was the protocol. Then people evolved and they came up with these protocols like NetFlow or IPFix. So what NetFlow and IPFix were doing was that they were aggregating statistics from a particular flow, okay? And now that we have learned about flows, can anybody tell me what is a flow? How do we define a flow? Yeah. Right. So like a broader definition is all packets that have similar set of headers, or at least few fields of the headers are similar, right? And the most natural way of abstracting flows is to think about the 5 tuples that are, that are unique for transport connection between 2 end hosts. So when there are 2 end hosts, there is a transport level connection between the 2, and all packets that are belonging to this, transport connection, which is a TCP connection or UDP connection, they will all have 5 tuples as same, right? So source IP, source port, destination IP, destination port, and protocol. So these 5 tuples will be the same for all the packets that are, part of this TCP connection or the UDP connection, right? So that is the definition of flow. And the tools like NetFlow and IPFix, what they were offering was that they were offering some aggregate statistics for each of those flows, right? So they will tell you that how many packets were there. They might tell you something about the jitter within this flow. They might tell you the volume of, like the number of bytes that were exchanged as part of this flow. But that's it, right? So in some sense, it's better than the link level statistics that you can extract, but it is still, you don't get the packet level detail, which is like, at what time this packet one arrived, what time this packet two arrived. You miss out all these details because that is an aggregated information, right? So the final frontier that a lot of researchers, argued, and this goes as back as early 90s, researchers at AT&T were arguing that the best way of extracting perfect insight from your network is to look at the packet level details, right? And I would say, like, maybe I should not give all credit to AT&T. There were researchers before AT&T as well who developed the tools like TCP Dump to, like create a mirror of each and every packet that you're receiving on the host. And you can create a dump of all these packets and then analyze those packets later, right? So TCP Dump was a tool that was already there, but then AT&T built a tool called Gigascope, which was basically streaming all these packets across the network into some collection server, and then using that, like, that data to answer different type of query that we were talking about, right? So the more evolved version of this, especially backed by the PISA targets right now, is the abstraction of treating packet as a tuple, right? So when we think of analytics, when you think of, like data analytics queries, you're always expressing those queries on some sort of tuple, right? So you have some tuple, then you apply a set of operations on top of that. That's a data flow pipeline that is very standard in analytics, right? So what networking researchers also converged on was that let's try to treat the packet as a tuple. That is the finest granularity at which you want to express these analytics queries, right? And what packet really offers is that it offers the standard header fields. It offers access to payload fields as well. But more importantly, with these PISA targets, it also offers access to some meta information about the network, right? And if you remember, I think, like you have now been exposed to how P4 and PISA switches really work. You do have access to a lot of meta fields when the packet is inside these PISA targets, right? So it can query or it can read the state of the switch and add that state into the packet header itself, right? So the state of the switch can be like, when it is enqueuing, then what is the size of the queue, right? So this is an information that is a meta information available to the packet, and technically it is possible to push this information into the packet's meta field, right? And I think, like, we also talked about in initial, like when we were talking about the hardware data plane targets, then we also talked about the features such as timestamp, right? So the time at which a packet got enqueued and time at which it got dequeued, this is the information, this is snapshot of information, is also something that we can add to the packet header, right? So now that the packet is not just carrying the information about where it is coming from, where it is going, what type of content it has, but it also carries information about which set of switches it is going through, or at what time it came, what time it left, what was the state of the switch that it observed, right? So all this in meta information is also available at the switch, right? So now, like, having access to this quantum of information can support all possible queries that you can think of from a network. There is nothing more fine-grained than a packet in a network, right? So that is the finest level of granularity at which we can express any type of network analytics task, right? And that is the granularity at which the community converged that, okay, this is the best granularity. Now let's figure out how we can make it work, right? And I think this is, like, this is just expansion of what I said before. So let's try to understand that with this type of abstraction, where we are treating packet as a tuple, how can we use that to express an analytics task? Okay. So we'll fall back to the same problem that we were discussing before, that we are trying to identify victims of a DNS reflection attack in a network. Okay. And the like the simplified version of this problem is that we want to identify if the DNS response messages coming from unique servers, like unique open resolvers or servers, are sent to a single host, and if that number is exceeding some threshold, right? So in some sense, like, in your network, there will always be hosts that are receiving some type of DNS responses, right? But if you're receiving too many of DNS responses from a wide range of open resolvers out there, then I think like if that number is exceeding some threshold, then that is something which is a suspicious event that's going on and worth reporting, right? And I also want to help you build intuition that why this distinct server thing is important. Because if, say, for example, the attacker chose just one open resolver to send all the attack traffic, right? So even before it can like attack the victim, in some sense it is attacking the open resolver itself, right? Because if the open resolver is the one which is responsible for receiving all these requests and sending all these responses, then like that one resolver will just get overwhelmed and your attack will not be as successful, right? So there is a lot of value in using as many resolvers as possible, right? And there is this network of resolvers that are out there that you can use, that are publicly available. You can send your DNS queries to them, and they're supposed to, or they're programmed to respond back to you, right? Yeah.
Those resolvers who are supposed to track them over level 3 or anything like that. Why would this be like something AT&T would implement instead of the resolver? So if the resolvers handling a ton of outbound egress data, wouldn't they track the job bill?
Yes, absolutely. So like there is a lot of it's a economics question as well, that why will they host it. First, I think like the best practice is that if you are AT&T and if you are hosting resolvers, you place a policy which only respond to your customers, right? So that is the rule number one. But a lot of resolvers out there are misconfigured or not configured well, so they don't have those type of filters in place, right? And and maybe we should take a step back, right? So let's think about that. When you are trying to access any website, where is your query? Where is your open resolver, or where is your resolver? Where is your query, DNS query going? It depends, right? So if you have configured your browser to use the DNS server of Google, which is 88888, if you have configured explicitly, then only your browser will send the request to that Google server, right? But otherwise, by default, most of the time, that DNS resolution, DNS configuration is provided by the network, whatever network you're signed up on. And in most cases, you can check today that it will be like, you will have a configuration where that is DNS server is mostly a local server hosted by UCSP, right? So in most cases, when you are sending a request, and if you're not explicitly configured your browser to send the request to Google or some other third-party resolver, your request will be going to a resolver here at UCSP, and you cannot use that to launch a massive attack, right? It's going to be like you need a lot of these resolvers to really create a volume that can overwhelm the third party. Otherwise, you will be bottlenecked by your own network or the bottleneck by the network that the resolver is operating in, right? So you really need a big list of resolvers. And this is something which is, I would say, is a bit of an open or known problem in the community, that internet is a big entity. There are so many networks, there are so many network operators. Not everybody is equally sophisticated to write the best possible safe configurations for the resolvers, right? So there are a lot of, and this is what the attackers are always looking for. They're always sniffing or looking for opportunities that, okay, where can I get this resolver which does not have the right filters in place that I can use for launching attacks somewhere else, right? And it's not always the DNS resolvers. Any type of protocol where you send small request size and the response size is huge, and you can redirect that response to your target of choice, and that can be used for launching any type of massive attack, right? So it's not just these DNS resolvers or open resolvers that are targets or platforms for launching these attacks. I think like recently there were some attacks where people identified, or when I say people, attackers identified vulnerabilities in the IoT devices, right? So think about all these smart fridges and smart, like switches and everything that you have. So there were these vulnerabilities that were there in these IoT devices itself, where the attackers were sending some small size requests to these devices, and they were amplifying the response, and they were able to manipulate where this response goes, right? And that's how, because there are millions and millions of IoT devices out there, so that just, even though the contribution of one specific IoT device to the attack was marginally small, but overall aggregate volume wise, that was a huge amount of traffic that was going to the victim IP addresses, right? So this is how these network operators work, or like these attackers really work. But if I am a network operator and my job is to protect host in my network, I need to run a query on the traffic that is coming in to figure out that, is there any type of anomalous traffic pattern going on here or not, right? And the example here is that if it's a DNS-based attack, then I'm interested in counting the number of DNS responses that I'm getting from unique resolvers or unique source IP addresses. And if that number exceeds the threshold, then I need to report that. I need to know who is the victim IP address here. So the way I would express the query for such a task is that I will say, like, packet stream. Packet stream is basically representing the stream of packets that are input here. And first thing I'll apply is that I'll apply a filter and say that I'm only interested in DNS response messages, right? So this is in line with the discussion that we had before, that there are so many ways in which we can express traffic. You apply a filter rule and you can express which portion of the traffic you really are interested in. Then we are interested in the unique DNS servers, right? So what I will do is that for all the responses that are coming in, I will count the pairs of source IP and destination IP, right? So how many pairs of source IP, destination IP do I have? And if I do a distinct, then I get the distinct pairs of source IP, destination IP, right? So suppose there are 10,000 packets coming in, I apply the DNS response filter, then maybe there are 100 packets that are corresponding to DNS responses. So I will have 100 pairs of source IP, destination IP with this first mapping operation, right? But out of them, maybe only 10 of them are unique, right? So when I apply the distinct, then I will, like, the output will be just 10 pairs of distinct source IP, destination IP. Is that making sense? Yeah. Okay. And then I will, because I'm interested in the count, right? So I'm not really interested in what source IP is sending the traffic. I'm just interested in how many of them are sending, right? So I will, from that pair, I will replace the source IP with 1. And for every destination IP, which is the host in my network, I will do this reduce, which is count. And for every destination IP, I will have a count of how many distinct source IPs are sending DNS responses to my network, right? And if that is exceeding some threshold, then I will report what is that destination IP, which is the victim IP in my network. Is that making sense? Make sure you understand, because we'll have a question on that in the final exam. We need to understand the logic behind it. So first of all, this is what we are looking at is a data flow query, right? So data flow has a tuple. You apply a set of operators on top of it. The operators can be stateful, they can be stateless. So stateful operators are operators like distinct and reduce. The stateless operators are like filter and map, because you don't need to maintain any state to apply them, right? It's a simple transformation. But distinct is you need to maintain some history of packets or tuples that you have seen in the past, and then apply that over some time reference window and compute these statistics, right? So I think, like, like the type of question that I will be asking is that I'll give you a data flow query and you have to explain me what really is going on. Okay. So make sure if you have questions, like, I'm not saying that you ask all the questions right now, but make sure you understand the logic behind how you're going to infer if you're given any type of data flow query. Okay. All right. So, like, this should give you a good sense of the requirements that we have from the network. We have a requirement that we really want flexibility in terms of how we express those analytics tasks or queries that we can use to extract what really is going on in my network, right? But then the next challenge is that, okay, I can provide you packet as a tuple abstraction. I can support you this data flow abstraction, but then can we really scale this, right? Because when we talk about networks, especially when we talk about really high speed networks, then we're talking about gigabits or hundreds of gigabits of traffic rate coming in, or data rate of packets, and then and that's just the packets that are input for one query. But as a network operator, you might want to run 10 queries, you might want to run 100 queries, right? So that leads to a big scalability challenge. That we want this flexibility, but this flexibility is coming at the cost of resources that will be required to execute all these queries, right? So now the question is that what should be the right strategy or approach to scale query execution? Okay. And now we'll go back to this familiar discussion that we have had in the past as well, mostly from the forwarding decisions perspective, but now we're talking about from the telemetry perspective, that we have these two set of targets at our disposal, right? We have CPUs, we have switches, okay? Now, when we talk about CPUs, they're very flexible, as we know that, if you want to do any type of match, you have flexibility that you can match on headers. You can also match on the payload fields, right? So now, okay, this is a refresher. So why is it easy to extract payload fields in CPU and not easy to do the same thing in hardware target? Can anybody explain me that? Let me be more precise. So when the packets, like, think about HTTP traffic, right? You know how HTTP work. You have, the TCP, and then on top of TCP, you have the application, which is the HTTP. And HTTP is basically, you have post, you have get, and all those things, right? So if I want to say, write a query, which says that for the HTTP get, extract the a refer, like part from this HTTP request, right? Or like the URL part of the request, extract that specific field from the HTTP. Can I do that in the hardware target? Can I parse an HTTP traffic in hardware target? Why? Is that impossible? Is that like, is what? What, like, why is it hard is what I'm getting at. Why is it fundamentally challenging if it is fundamentally challenging? Okay. Okay. Yes. 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 So I think, like, you folks have already been exposed to how you can write different type of custom parsers in the hardware, right? So like, when you are expressing a parser, it's like a finite state machine, right? And the important thing about finite state machine is that it is finite. And being finite is important in the hardware targets, because you have these, you can't reuse the resources for different set of operations. You have to have one-to-one mapping between the resources that you're using and the operations that you're performing with those resources, right? So if you express a parser which is doing certain set of tasks, you don't have this flexibility that, okay, for one packet I will apply FSM1, which is finite state machine 1, and for the other packet I will apply a completely different finite state machine, right? So there is a lot of conditional variables when we think about these different type of protocols. Technically, if I want to design a hardware target, I can design a hardware target for HTTP packets. Theoretically, it is possible. It just means that I need to put in more resources so that I can support this, like the dynamic set of fields that I have to parse based on different conditions, right? So if it is post, then I have to apply a different type of parser. If it is get, then I have to apply a different set of parsers, right? So that is one challenge in terms of, these conditions, or how do I handle the dynamism that is part of these header fields or these packet fields, right? The second thing is that how deep I need to go, right? So more deep into the packet layer I go, more state I need to maintain, right? I need to extract that and put it into the packet header vector, right? So there's also a limit on how many fields or how many bits I can use for carrying that information that I'm parsing from these packets, right? Because that's kind of like fundamental. That is the size of the bus in some sense. That what is the max number of bits that you can apply processing in parallel in this hardware target, right? So there is this finite limit on that as well, that I don't have infinite bandwidth in terms of how many bits I can extract from a single packet and apply processing on that concurrently, right? So these are two reasons why it's like, we should not say that it is not possible to extract header fields from beyond layer 4, but it just gets complicated in terms of the type of conditions that you will have to support, and the depth of, or the amount of information that you have to preserve in a packet's metadata or packet header vector, right? So these are the two reasons why it gets very challenging, but theoretically it is possible, right? And again, I think, like, just from the cost perspective as well, I can design that hardware target. That's not a problem. It's just that it will be very expensive, and too expensive to be feasible or practical. And this is the difference between specialized targets versus generalized targets, right? So PISA is a generalized target. It is used for a wide range of applications, and parsing or telemetry is just one of the many applications that it can support. But there are these vendors out there which are maybe designing hardware targets specific for a certain type of application. So there are these vendors who are selling hardware targets for network security, right? So there it might make a lot of sense to extract fields from, say, DNS protocol, extract fields from HTTP protocols, extract fields from like at least a subset of fields from each of these different protocols where the parsing is difficult. So you can technically do that. And it's just that it will cost a bit more, right? And that's why these specialized hardware targets are more expensive. And the approach is to, make sure like maximize what you can do with these generalized targets because they're relatively cheap, right? So anybody can give me a sense of, when I say cheap, can anybody give me a sense of how cheap these PISA targets can be? Maybe I've discussed that in the class before. Okay, no. So how expensive do you think a switch which can support, 3 to 6 Tbps of traffic total can be? 200,000. Price is right. Anybody else? any guesses? What do you think? 200,000, 1 million? I would say 200,000 is expensive. So bid low. 2,000. Okay, you're getting close. Okay, so let me reveal that. So so one, don't quote me on the exact price because these prices change and depends on which vendor you're buying it from. But what we bought for our lab, we bought a switch that is capable of handling 3.2 Tbps of traffic, and that is just $6,000. It is cheaper than a server, like a high-end server that I buy for my lab, right? And that can handle 3.2 Tbps of traffic. It has 32 different 100 Gbps ports, and I can do it. I can use it for whatever I want, right? Yes.
Just for how many terabytes per second could one of these?
It's way more than one switch at Google needs to handle, right? So this is something which, like 100 Gbps is a link capacity that is very common. So, like 32 ports is quite dense overall. And so they also have a version which is, 64 100 Gbps ports, and that's, a couple of thousands more expensive. So, like it's not a linear increase as you try to increase the number of ports. It just is a good idea to have like high port density, and then you if you want more ports, you can just buy more switches.
Is the thing you want like industrial capacity to be installed?
Yeah, there's nothing more than that. So 6.4 Tbps is the max that you can buy out in the market, right? So that's way cheap. Like when we say cheap, that should give you a reference, right? Because before that, when you were trying to buy a Cisco device or a Juniper device for the similar capacities, you're talking about $1 million, right? And there are, as I said about this, specialized targets as well. So if you're focusing on some specialized target that are, like maybe supporting these telemetry functionalities and trying to extract all these complex header fields in the hardware switch itself, then those are still $1 million targets, right? Because the biggest, the cost of all these chips goes down based on the economy of scale, right? So if you have a bigger demand, which means like if you're a generalized offering that you are able to support a wide range of use cases, then you will be able to sell an order of millions or hundreds of thousands. I don't know the exact numbers, but if you are selling it at scale, then you can make it cheap, right? So these specialized hardware targets, there are fewer customers of that, then like the cost is going to be high, right? So I just wanted to give you that perspective that if I compare a CPU, a reasonably provisioned CPU, or a server CPU based server, 6,000 switch versus 6,000 CPU, I can process a lot more. Of course, I have a lot more flexibility when it comes to the CPU, but it's like these prices are comparable. It's not orders of magnitude difference in terms of price. Okay. So something that is important to point out here is that when we talk about state, right, and when we talk about these data flow queries, we discussed this operator called distinct. We discussed this operator like reduce, right? So these are stateful operations. When you say stateful operations, you need memory to perform that stateful operation, right? And there are 2 or 3 different types of memories, right? So one is TCAM. We talked about TCAM. We talked about this wildcard entries, and like that is one unique capability of TCAM, right? So you can support these wildcard entries with TCAMs. But then there are 2 other type of memories. One is called SRAM, and the other is called DRAM, right? Are you folks exposed to these terms, or this is the first time you're all listening to it? Some of you are exposed to it. Okay, so from networking perspective, what is important, or like as a rule of thumb, is like TCAM is the fastest. SRAM is also fast, but it does not support the wildcard, right? So SRAM, the delay in read and write operations with SRAM is of the order of nanoseconds. And order of nanoseconds, as we maybe in initial set of classes we discussed that like order of nanoseconds is basically line rate, because the amount of if you're getting these millions of packets, the time budget that you have for a single packet is of the order of nanosecond. So if you can read and write to this memory in order of few nanoseconds, then you can consider that as a line rate operation, right? But when you are talking about CPU, you are talking about DRAM as the memory that you have for access, right? DRAM is slow compared to SRAM. So there you have to spend multiple CPU cycles to perform the read and write operations. And CPU cycles for gigahertz, processing, that's order of few microseconds, right? So, or maybe, well, it's order of nanoseconds, sorry. But then it there are multiple set of instructions that have to be performed. So most of the time, the read and write operations are in the order of microseconds, because this is a shared resource, right? So you're queued with all sorts of processes that are trying to access all these hardware resources on the CPU. Then that all contributes to this overhead. Then there is context switching between different type of processes. All that contributes to high number of CPU cycles per operation, and that increases the cost or time it takes to do the read and write operation. Oh, you had a question? Oh, okay. So this is and also I think I mentioned I didn't talk about the actions. So when we think about CPUs, we have complete flexibility in terms of what type of processing or transformation you can apply on a packet that is coming in. But when we talk about a hardware target, a data plane target, we discussed before that there are these finite number of ALUs that are available. So the data plane target is these stages. Each stage has fixed number of ALUs, and there is limited programmability available for those ALUs, right? So you can program that ALU to support a add operation, a subtraction operation, maybe do some type of bit shift operations, but that's it, right? You don't support floating point operations. You don't support the division operation, multiplication operation. So there are those limitations in that sense. And the SRAM versus DRAM comparison is that SRAM is fast, so that's a good thing about SRAM. But SRAM is extremely expensive, right? So the cost of gigabits of DRAM is same as cost of megabits of SRAM, right? So that's a rule of thumb comparison. Don't quote me on the exact numbers, but that's a rule of thumb that it's orders of magnitudes expensive compared to the DRAM. So DRAM is cheap. If you want operations that require gigabits and gigabits of memory, you should be using DRAM. But if if you're trying to do things in the hardware target where you want to have nanosecond delay in terms of read and write operations, then you are limited with the amount of memory that you have available in that chip area. Okay. All right. So now with this context that so far we talked about this set of problems where we need to have this flexible telemetry enabled, where we want to query any portion of the traffic, extract any type of extra aggregate metric from the traffic, right? But we know that scaling that is going to be challenging. Now we have two different type of targets with distinct set of capabilities, right? Now what we're going to talk about is that what design choices do we have at our disposal when we're trying to build the telemetry systems, right? Or in some sense, when we're trying to think about that, what is the right way of executing these queries? What is the right design choice? So we are going to talk about how the community has evolved, what type of solutions are out there, and then we will zoom in on a couple of solutions, okay? So the first idea, which a lot of people had, is also very intuitive and straightforward, is that whatever packets you have in the network, just dump them, take them into some CPU-based cluster of servers, and then we'll figure out how we will scale it, right? So I mentioned Gigascope, and you notice that it's 2003 submission, paper at SIGMOD. SIGMOD is a very reputed conference in the database community. So that research paper was more about how they built this big database system where they're ingesting all the traffic from AT&T's network, putting it into this rack of servers, and then applying all the analytics there, right? So there are pros that because you're taking in all the packets from the network, you have all packet fields available, right? So this packet as a tuple abstraction that we were talking about, that is something that you can support. You can write queries at that granularity, right? But the challenge is that this is really, really hard to scale, right? I mean, this was a very popular project at AT&T. This was very attractive for a lot of graduate students working with or collaborating with AT&T, because that was the only place where you had access to such fine-grained data, right? Like nobody was capable of collecting such fine-grained data at their campus network. So everybody was going to AT&T to do research and try to, like a lot of fundamental research was supported because AT&T built this type of infrastructure back then, right? But then, as AT&T realized and everybody realized that this is very, very expensive thing to do, right? So just to give you some number, if you're talking about just 100 Gbps link for 1 hour, the footprint, the memory footprint here will be 45 terabytes, right? That's a lot of cost to bear in 2003, right? So you have to take into consideration the storage costs have significantly reduced in recent years, but that was not necessarily the case when we were talking about 2003, right? So, and I think like beyond cost, something also that you need to take into consideration is that I can take in all this data, but I cannot process this data in real time, right? It's not just that the storage is a problem, it's also that I cannot process this much of data in real time, right? Because we're talking about 100 Gbps, so like tens of millions of packets coming in, I cannot process it that fast, right? So it's not suited for real-time analysis, but it was great for offline analysis, right? So if like this type of data set resulted in understanding the fundamental nature of how different type of end hosts are talking to each other, what is the pattern, how many bytes are exchanged, is there any unique spatial temporal properties exhibited by these type of connections. So this is all fundamental research that was enabled by it, but it's not useful as a network operator if I want to detect a problem now. I can do this analysis and tell you like, oh, last week we had some attack, right? But it's not as useful as a network operator. So what can we do? So as we explored the first solution, there the approach was send all packets to the server. The other extreme of the design spectrum is that let's do everything in the switch, right? And this is something which was inspired by, I noticed there is a bug here, so I need to fix that. OpenSketch is not Sigmod 03. OpenSketch was SIGCOMM or NSDI 2015 or 2014, right? So mistake there. But what's important to understand is that all these solutions, were inspired by software-defined networking, right? So when software-defined networking came out, we had these programmable hardware targets, and people started exploring that, oh, rather than sending all this traffic to some CPU where we can do flexible processing, what if we leverage the capabilities provided by these hardware targets and execute the queries in the hardware switch itself, right? That's a brilliant idea if you can do that, right? Because now if you're able to execute all these queries on the switch itself, then you don't have to send anything out. So you don't have that cost of sending traffic. You don't have the cost of storing all the traffic. You get the answers. The challenge is that, as we know, that there are so many limitations in terms of what you can do in the hardware target, right? So there is limited, they're offering limited flexibility. You can only support certain type of operations. You cannot support all sorts of queries out there. And also there is limited scalability, because we know that for doing things in the hardware target, you have to rely on SRAM. SRAM you only have available at the order of megabytes, right? So that means that you won't be able to scale easily. And as we this is something that we will dig deeper in later lectures as well. But if you have limited memory, and if you are trying to do this counting operation or reduce operations, then that will affect the accuracy of the query, right? So you have to play around a bit, that either you just handle small volume of traffic with this type of approach, or if you want to handle a lot more traffic with the same limited amount of memory, that will cost the accuracy of these queries, right? And maybe to an extent that these queries or this approach will not be useful at all, right? So now we talked about two different extremes here. One extreme that send everything to the CPU, the other extreme do everything at the switch. But then people also started exploring that maybe we can do something in the middle. And one approach that was explored heavily, and Everflow is a research, in fact, Everflow and DShark, both these research artifacts came out from Microsoft Research. And what they proposed was that maybe it's not as useful to look into the payload fields, especially when we're talking about data center networks and stuff. We know what the payload is there. Like it's not a lot of unpredictable, like most of the payload is predicted or predictable because it's part of the data center networks. They are the ones hosting all these services. They don't care about the payload as much, but they realize that the headers and the meta information with these headers is the one that they should care more, right? So at what time the packet arrived at a particular switch, what, like how many, like what was the trajectory that the packet followed, right? So if I have a timestamp of packet from switch 1 to switch 2 to switch 3, and if I don't see the packet on switch 3, then I know that it probably got dropped between these two links, right? So this was the information available, yes. Yes, and it depends on what type of network you're operating, right? So it's not if you are Microsoft or Google, because you are the content providers, you are creating that payload. But if you are an operator here at UCSB, and if I'm looking at the payload of each and every student here, that's a privacy violation, right? So we should not be doing that.
In 2003, AT&T was granting students access to everyone's payloads.
Yes, I mean AT&T can do that even now. So we have a research collaboration where we are trying to get an agreement with AT&T, and one point of contention is that it is possible that when they share the data with my grad students, some PII information can get revealed, right? And I'm pushing back that no, I don't need that because my research does not require looking into the PII. But if I get access to any data that has personal identifiable information, then I have to go through a completely different process to make sure that I am holding that data with utmost responsibility and not making sure that that data does not get leaked from me, right? And that's a completely different beast in terms of handling data or managing data. And but AT&T or any, like, I'm not just blaming AT&T, it's like any ISP, right? Like, if they want whatever they can extract from the network, they will extract from the network, right? So, and this is also a fundamental contention that the network operators, these ISPs have now with the encryption protocols, that they invested heavily in all these type of network devices that they can use to optimize their network, which relied heavily on doing deep packet inspection, right? So for example, if they want to do some type of discrimination between Skype traffic versus peer-to-peer traffic versus YouTube traffic, right? So it was very easy for them. They will just do a deep packet inspection, which means that look into the payload fields and figure out, oh, this is HTTP, it says youtube.com, then I know for sure that this is YouTube, right? And then they will apply policy A for YouTube, they will apply policy B for Skype, and something else for something else, right? But then when now everything is end-to-end encrypted, it just gets a bit difficult for them, right? So yeah. Yes. So they invested in it, and so that was a complete market of its own, right? So there is this entire cottage industry around building these type of expensive devices. Not everything is ethical or legal there, but these are the practices that are out there. And I'm not saying that AT&T is doing that, so don't quote me on that. I'm saying that this is a capability that a lot of ISPs have, and they can do that. But I'm, because this is a recorded lecture, I can tell you, I am in no knowledge whether this is a practice or if ISPs are doing that deliberately. But if they want, they can. Okay. I'm avoiding my liabilities here. Yeah, any question? Okay. All right. So, so Everflow and DShark both focus on these set of ideas that let's just focus on the headers. Let's focus on the meta information that is available from the headers. This was great. But again, when we take off the payload and we just have the headers, but and if you're looking at headers for each and every packet from each and every location or each and every switch in the network, that is still a huge amount of data. Yes.
Of all the software, Wireshark, does it use this technology?
Yes. So in Wireshark, so DShark is inspired from Wireshark, right? So DShark is basically, in some sense, it's an acronym for distributed Wireshark, right? So technically, when you think of Wireshark is built up on top of this TCP dump as a tool, right? Or so that's a tool for mirroring the traffic that is coming on your interface, and when it comes on the interface, you create a copy and send it to the user space, and then dump all the information, right? So DShark was inspired from it, but it's distributed. So if you're interested, you should read that paper. But I think the key challenge that they're trying to address is that they also want to extract a lot of meta information from the packet, right? Like, where it is, what type of policies have been applied on that packet, like that will be useful for their analytics task to figure out whether there is some type of problem in a particular link on a particular device on a particular interface, right? That's the type of debugging that they're interested in. Okay. So there is another line of work, and this is also very exciting because people realize that maybe it's not possible for us to run all types of queries on the network data in the switch. It's not possible for us to take all these headers from the network, from these switches to the CPU and do real-time analytics or any type of processing on the data. So they thought about the idea that what if we, configure this hardware target such that it compresses as much information as possible in the network traffic, right? And this is actually very interesting. And I won't say that the Starflow paper that I'm talking about focuses explicitly on compression. It focuses more on extracting. In some sense, it's one type of compression, but it is not selling itself as a compression work, right? But what is important to note here is that when we talk about network traffic, you have to understand that network traffic, the bits, the different fields that we have are part of a particular protocol, right? And protocols are basically finite state machines, right? So you are in particular state, you have a trigger, you go to a next stage, or you stay in the same state, right? So when think about TCP, so the sequence numbers, right? So the next packet that is coming in will always have an increment by a fixed amount for the sequence number, right? And the acknowledgement packet will always have the the number that is corresponding to the data packet sequence, right? So these things are predictable, right? When these things are predictable, that means that provides an opportunity to reduce this redundancy in the data, right? If you have something predictable, maybe you can transform the data in such a way that you can reduce the randomness in the data, right? And maybe I'm talking a bit abstract because you folks are not as exposed to the compression ideas in general. But let me take a step back. When we talk about compression, we talk about like the compression is only possible when you have some type of redundancy in the data, right? So when we talk about all these different type of algorithms out there which do compression, they all focus on doing some type of transformation on the data such that you reduce the randomness, right? So if there is, say, suppose the data stream is a time series where the number is increasing by one every time, right? So you have 1, 2, 3, 4, 5, 6, right? You look at that data as is, you will say like, okay, there is a lot of randomness in the data. I mean, like, I look at this data, I compute the entropy of this data, that's very high because each value is very different, right? I don't see any repetition. But if I just transform this data by taking a delta between consecutive values, right? So then the data that I will see is just 1, 1, 1, 1, 1, 1, 1, 1, right? The entropy of that is extremely low. I can just encode this entire time series in a couple of bits, right? So this is an example of how the network traffic has the potential of this this skewness, and that's something that we can do to apply some transformation on the traffic, make sure that the distribution has as low entropy as possible, which means that we can compress that information in much smaller number of bits, right? And this is I'm exposing you to this because this is something which is an ongoing research in the community. In some sense, this is kind of like the next goalpost that a lot of researchers have set for themselves. Like, one, can we use PISA targets to compress this packet stream with as much compression efficiency as possible, right? That is one research problem that people have posted. And it's easy to do this type of research. You're given a data set, you're given a PISA target, go figure what is the best algorithm out there, right? The second approach that a lot of researchers are exploring is that do I need to tie myself to a PISA target? Can I think of a completely different hardware architecture that is custom designed just for compression? And can that do anything better in terms of compression? So this, now you might be wondering, why will I just design a custom hardware just for the compression task? Because being able to collect each and every packet from the network for a relatively longer period of time is very, very important for fundamental research, right? If I want to train any type of machine learning models, I need a lot of data to make sure that I'm able to train all these type of complex learning models, right? So there is a huge motivation in the networking community that we need a lot of data. But then when we talk about a lot of data, it just goes out of hand when I'm trying to naively store each and every packet in the network, right? The approach that Gigascope had, the approach that Everflow, DSharp, all these type of like systems, they had this approach, but then they're like really, really hard to scale. So that's one frontier. I just want to give you a taste of the research firm that the community is looking at as well. That the next frontier is to figure out what is the right way to compress all this data such that we can train these complex machine learning models for network data that is worth like weeks worth of data that are from a particular network, right? So that's kind of like the ultimate goal that a lot of researchers have. Okay, so the final approach that I'm going to talk about is a hybrid approach, right? So one extreme is that send everything to this server. The other extreme is to do everything at the switch. Somewhere in the middle, what we can try to do is that try to figure out that what is the best we can do on the switch such that it reduces the load at the server, right? And that is something that has been explored in past couple of years. That is also an active area of research, but there are a couple of systems out there, Marple and Sonata, which talk about how can we, like if you are given a particular query, let's try to figure out what portion of query I can execute in the switch and the remainder part of the query I can execute in server, right? And this is a non-trivial problem to figure out how should I partition a given query to make these type of decisions. But the gist is that I don't have enough resources on the switch, so I cannot execute the entire query in the switch, right? But executing this entire query in the server means that I have to take all the traffic from the switch to the server and then apply, process these millions and millions of packets at line rate. That's extremely challenging, right? So this is the approach that the community has converged on. And in the next lecture, we are going to dig deep into this specific approach of building network telemetry systems. We will specifically focus on the system called Sonata, and we'll talk about that how it uses these pizza switches to scale the execution of queries, right? What type of ideas, like what are the challenges that are associated when we're trying to partition a given query and execute as much of it as possible into the hardware target, and what benefits are possible, right? Is that enabling us to reduce the load at these servers by 1 order of magnitude, 3 orders of magnitude, how many orders of magnitude is possible, right? So we're going to talk about those challenges in the next lecture. Okay. All right. So questions? I guess we're getting close to the end. Yes.
So once the switch finishes processing the result to the CPU, wouldn't that since CPU is kind of relatively slow compared to the switch, wouldn't that cause the data to be accumulated and then overflow?
Yes. So absolutely, it cannot execute the data at the same speed as the switch, right? But when we talk about the stateful queries, then there is always a reference of time associated, right? So as a network operator, I might not be able to make any decisions at the granularity of microsecond anyways, right? So I need to know whether there is a victim to this attack in my network in the order of some coarser Windows granularity, right? So it can be 1 second, it can be 1 minute, it can be 15 minutes. 15 minutes and all those things are really, really old school things, right? But even enabling things at the granularity of 1 second, 5 seconds is completely, dramatic when it comes to telemetry systems. So that's why I would say, I would calibrate that and say it's not real time, it's near real time, right? But if this is about a human operator, they cannot discern anything less than few milliseconds, few tens of milliseconds. Okay. All right. So in the next lecture, we are going to talk about Sonata as a system in details. All right. Okay. Thank you, folks.